And I'm back. It seems to me every time I try to do one of these videos I get hung up on some weird detail that sort of derails me for hours, and then I sit down and just chug into the code. So this might be the start of a separate video where I actually describe and talk to you guys about how I solved everything I was trying to do in the last video. So what I did want to do was use behavior trees. I wanted to use behavior trees so that the enemy entities, the NPCs or the enemy AI, could make decisions in the game, and I wanted to combine that with Ashley so that I could have Ashley entity systems to implement the behaviors of the enemies and components to kind of keep track of state and not involve some kind of state machine or something like that, and not keep everything in some class that sort of not keep everything in an enemy class or anything like that. Just keep the entities lightweight as they're perhaps supposed to be. So what I wanted to achieve basically was, and if you never had a look at the behavior trees in libgdx, it's not very complicated. You have a behavior tree which is inheriting from something called a task of type T, and the type T, the generic type argument here, is the blackboard object, and this is a concept in behavior trees. The blackboard object is the shared data for the tree, where you like, if you're looking for something, you have to store the result or some state in the blackboard object so that other tasks that you would perform can have a look at that data later. So I wanted the blackboard object to be an entity, and I wanted the syntax to build the tree to be a bit more convenient. It's very convenient using libgdx behavior trees. You could write the trees using text like this described in the documentation, so like lines with tasks and comments and stuff like that. And this is quite nice because you could then implement your classes, import them into the code, and just write text files. And having them as text, basically as code, you could change the behavior or share behavior or modify behavior without modifying the code. Now my games aren't at that place yet, and creating tasks using constructors and building objects is a bit wordy, to say, to put it mildly. What I wanted was to use Kotlin domain-specific language support, type-safe builders, to basically make a domain-specific language. So this is where I am. So I've got this object tree. This is just a static object that's accessible everywhere, and I have this function bt. It's not a good name. Let's get enemy behavior tree. There you go. So I wanted to build it this way, like tree, entity, and then selector. This is a concept in behavior trees. Basically, a selector tries to execute tasks, and the first task that is executed just simply returns. I'll go into detail on how the tasks actually work to enable sort of moving on to the next one all the time and sort of getting back to the first one, etc. So I wanted to be able to say something like, okay, first you do this. That's a convenience method, basically. First, and this, I might change the name of this function, entity do, and that's a component in Ashley, an Ashley component. So let's have a look at that. The amble component. It's a specific, it's inheriting from a specific task component, and this one implements it inherits from component and also poolable, because we recreate and this is part of the pooled engine stuff, so you need a reset method to sort of say it. And as you can see here, all the task components will have this property: status, task.status, task status, running. And this is part of the behavior tree implementation actually. So the behavior tree will execute tasks in order. So this one, the selector, will try the first one, and while this is running, it will return the status of running all the time, unless we somewhere change that variable to be failed or succeeded. So it could possibly succeed. What does that mean in the case of ambling? Well, that won't ever happen. But the cool thing with the selector type of task is that when this task fails, it will then try to do this task until this one fails. So it's running, but in this case, the seek player task, it won't actually fail. It will succeed when the enemy finds the player. So I invert the result of this one. So when the enemy finds the player, this task will fail. So it will go down to this one, which is also inverted, the chase player. And then when it reaches the player, it will try to attack the player. And this one fails if the player moves away. So as long as the player is actually in range of the attacking enemy, it will continue attacking the enemy. I think this is quite readable, and I also have other convenience methods here. You could go right in here and just do add something like then. And to be clear, the first method up here actually adds this task first in the list of tasks to execute here for the selector, but the other ones just do the same thing. They add the task at the end of the list, so it's in order basically. These are just convenience methods to make the code look nicer and more readable. So when I have a look at this code, when I look at this code, I want to immediately know what's going on. So it's like I want to immediately know what's going on. So I have a look at it and I say, okay, there's a selector. It's going to do every one of these in turn. First this one, then, and then lastly. So I could add a sequence here. And that sequence. Oh yeah, sorry, I don't have to do then. I could do sequence. Okay, I don't really like the syntax of this, but if we go into that, we can see that this one just adds a sequence to the thing. I should probably change that. I'm not entirely sure how I want the syntax to be. It's not fully formed, so I could just do first some task here, etc., for the sequence. But we'll do with this particular behavior tree. Pretty simple. The enemy just runs around, does nothing. Intermittently it will try to find the player. If it finds the player, it will chase the player, and then it will attack the player. Let's have a look how this looks in the game, in practice. Clinging is my cup of tea. Okay, here we are in the game. The minimap is going, and here's a cluster of enemies. Let's go have a look. And as you can see, they have these little circles. These are debug circles. So it's yellow. It's found me. So it's gonna get closer to me. Now it's close enough to attack. I move away. Immediately the enemy will start ambling instead. Now it's seeking, and for some reason it's still walking. I'm gonna have a look at that. So it's trying to find me. As you can see, they move through. Oh, these guys have found me, and the group behavior of them, everyone's starting to chase me if other enemies around them also chase me. And let's I'm gonna shoot these guys. Cool, huh? So let's have a look at how this works really. So the tree here, this is just a function, and these functions aren't very complicated. They're a bit complicated because this is some Kotlin syntactic sugar stuff. So this is called a function with a receiver or something like that. So basically we say here's a function tree, it takes a block, and the block is a tree builder with no parameters and returns the unit. And this function is actually create a new tree builder, apply this block, apply is a method in Kotlin, and block is a function, so this function will simply rerun, and then we call the build method on it. Okay, what does that even mean, right? So let's have a look at it. Tree entity. Okay, we'll go into the tree builder, and the tree builder inherits from task builder, which is an abstract class, and the build method simply returns a behavior tree with the root task, and it's got this method add, and it can only contain one task. So the root task is a single task. But what is it? So let's go to task builder, and in the task builder we have this abstract class add, which is overridden in the tree builder, and then I have these methods for adding sequence, selector, parallel, random selector, random sequence. I could just as easily just call the add method for the task and just call these methods outside of the class. Never mind. So basically what we're doing here is, okay, selector is a method on the task builder. It adds a selector block or selector builder, which it builds. So the selector builder, what's that? It's a composite task builder. And if we look at this one, it contains the convenience methods for first. So first actually adds a task at the first spot in the list, the mutable list of tasks, and then we do some other things. Okay, this is pretty basic. This is just to build the overarching logic of the tree using the normal things you have in libgdx behavior trees, and behavior trees are really cool. I'm gonna link to the article on Gamasutra, that Chris Simpson has written, and this is an old article, but it still contains great information for behavior trees. And you can also read the documentation to understand what all these tasks do. And you have decorators and stuff. I just want to be able to write that in a succinct syntax, something that's easily readable. This is just half of the cool thing about what I actually managed to do here, because the really cool thing comes later. The really cool thing is inside here, entity do. Let's have a look at this one, because I'm kind of stoked about this one. This one is more complicated, it would seem. Here are some methods I'm not using anymore because I figured out how to actually do this. I started building trees that sort of check, do you have a component, etc. But I want the behavior tree should be as simple as possible. You shouldn't need tons of branches or leaf tasks in the tree to implement the logic that you want the AI to have. So let's have a look at what I did to get around all this and make it happen. So here's we got this inline fun reified T task component. What does this even mean? This means that inline means that Kotlin copies the entire code into the call site to be able to handle the typing of everything, because Java does type erasure on generics. This is a bit complicated. It's out of scope talking about the type system of Java and Kotlin, but it's really nice. This means that when I do entity do chase player, it changes this entire call into this call. So we do entity component task builder, and we into that we send this the type of T, the Kotlin class, then the Java class thing. So what's going on here? Let's go into entity component task builder. Doesn't seem that complicated, does it? It's a builder that builds tasks of type entity. It takes a component class in, and the build simply creates an entity component task with this type sent into it. So this is a class of type T. Okay, this is still kind of confusing, isn't it? Let's have a look at this entity component task. Here's the secret sauce. The entity component task of type T, where T is task component. So this is my special class that implements poolable and component and stuff like that to be able to reset itself. It takes this class argument and returns an entity task. The entity task is a special task. It just contains a reference to the engine and some entity. Okay, good. So what's going on here? Yeah, we have a mapper for this particular component type. The mapper here is allowing us to get the component if we need it. We'll look at that in the system later. And here's some overridden methods from the behavior tree stuff. So this is a part of the behavior tree implementation, basically. You can just override it and do whatever you want. This is inheriting from leaf task. So here we go, entity task, private model. Okay, start. We add to this entity at the start of this particular task. This is called before it runs the execute method on the leaf task. So on the start method, we add this particular component. And here's why we need the poolable stuff. So it resets the component, it pools them, and sort of says, okay, give me a component, add it to this entity, and then it calls the start method here on super. It doesn't actually do anything. And then on the end of the task, when we've finished executing, and the task has either failed, succeeded, or been cancelled, we remove the component. And on reset we do remove. We always do remove because on the start we always add the component. And copy to, I'm going to implement that later. This is to share trees and get copies of them and have them in a behavior library, etc., etc. And then we have this method, execute, return status. Do you remember that status property? This is the one running. So what's going on here? Well, the tree here, the tree just executes, just runs this method on every leaf task when it gets down to it. Just does execute, and that method is supposed to return some kind of status. So how is this actually used in the game to enable the enemy entities to run around and actually do something interesting and try to fight the player, etc.? Well, that is happening thanks to the AI systems. So let's have a look at the ambling system. So the ambling system is an Ashley iterating system that gets all the entities that have the amble class and the enemy component. So the amble component, I renamed them to remove the component thing, just to make the syntax look nice as you do entity do amble. I'm gonna figure out a good name for the entity do method here, so it gets more natural. I want something that seems like a natural language. And if we look at the system, then let's have a look at it. For every entity, it gets the amble component, checks the status to see if it's running, because it shouldn't do anything if it's failed or succeeded. And then it checks if the direction vector on the enemy component, the direction vector is simply a unit vector that says which direction the enemy should be moving. And if that is 0, that means we don't have a particular direction set yet, so we randomly generate one, and then we subtract the delta time from the cooldown property, and if the cooldown is below or equal to 0, we return failed. We could easily return succeeded. Yeah, perhaps we should. It doesn't matter. This is the indicator what this task is. Like, I'm done. Which makes it very useful in a selector. The selector will be running this task until it's failing, then it will try the next one. So that's probably why. So okay, so the ambling system, look at the code for the ambling. It's like less than 10 lines of code. It's not inside one system. I wish I had the I think I have the old system. Obviously I do have the old system somewhere. I've got it in Git. I'm going to I'm not going to go back to that. So, and this is a behavior tree system. This is the system that takes all the entities that have a behavior component. This contains the behavior tree, and it steps the behavior tree. Okay. Then we have the seeking player system. This was part of the enemy control system before. So this code is longer and more advanced because this one actually uses raycasting in Box 2D, and it sort of keeps track of it if we found a player or not. And if we found the player, we return succeeded, or if we find another enemy that is already chasing the that's what the code should look like, really. So if the closest enemy has this particular component, then we've found the player. Eliminate an if statement, keep it in else if. That's not nice. Or is it? Yeah, maybe. So this is riveting once again. Watch me reformat the code to be nicer. This is one of the more complicated pieces of code I've written for this particular game, the seeking thing, raycasting and stuff like that. So let's go back to chasing the player. So if we go back to this particular system, the chase player system, so this is for all the enemies that are chasing the player, obviously, and we just check if we are running, and we try to we get the player position, and we calculate the distance, and if the distance is less than 5, and this is actually the length squared. It's not the actual distance, but it's quicker than calculating the hypotenuse of, because I don't have to do a square root of anything, so I save some time here, but it's probably not an issue. Just figured I'd do that. So if we're close enough, this succeeds, and you know what that means, it goes on to attacking. Otherwise we'll just set the speed to 3.5, and we set the direction vector to be the direction of the player. And then we go to the attack player system, which is simply just trying to attack the player, and it has a cooldown, so it can only perform like some number of attacks per second, whatever, and it subtracts this and waits, and if the player actually gets away during this time, it says failed for this one. Otherwise it'll just keep attacking, right? Simple as that. So I just wanted to add a small thing to my user interface down here. I'm gonna do a small player health. Let's put that in here. Okay, string interpolation. Let's do player dot health, like that. Here we go. And we'll do targets left. Do we want the splatter count? Yeah, we want the, and we do enemies left. I can't spell for some reason. I'm gonna do a little formatting thing. Well, let's have a look at what the game looks like right now. So the point of all this was that I wanted to write behavior trees in a simple and understandable way, and I wanted some way to be able to move logic from the behavior tree tasks. I didn't want to write a bunch of tasks and stuff like that. I just wanted some kind of generic, because I'm doing most of the logic inside an Ashley entity system anyway, so I wanted to keep it that way, so everything is made the same way. And here we can see the enemies coming for me. Let's shoot them. And I'll go up here and I'll navigate this to find the target. Oh, new level. There are more enemies over here. Tons of them, actually. Where's the next target? It's over here. A 160 enemies. The thing is, you could actually just... Oh no, they're attacking me. Ah. Oh, this is scary. Cool thing is I can potentially just lure these guys away from the targets, because now I don't have this box 2D sensor thing set up actually, which makes their poorer at discovering me. Oh, here we go. Where are the targets? Anyway, I got lost in my own awesome little game. How about that one, eh? So let's have a look at the backlog for the game, okay? The backlog. Player damage, enemy attacks. I've done player damage and enemy attacks, and also refactored the entire AI system of the game. This is pretty cool, isn't it? You can check out the code on GitHub. I'll link to the articles I've been inspired by for this in the description of the video. And the next thing we're supposed to be doing, I'm gonna go to my stack edit editor. Never show your browsing history to people online. I'm gonna go here. This is not it. I'm gonna edit this one out. I'm gonna go here. I'm gonna do that. I'm gonna go there. Let's do the readme. Yeah, so let's have a look at the backlog and see what we've done. Yeah, this is done actually. And I'd like to add done. There's no play death or anything. You could just keep on playing until time runs out of the entire universe, obviously. This doesn't actually mention the implementation of the AI and the changes I made there. It's not really that important. So what do we got here? We got controller support, twin stick shooting, towers, etc. The cool thing is that we could, using this system for the AI, I could expand the behaviors of the zombies to be more advanced easily. So now I should just add the features I think vehicles are nice to have. but maybe not necessary, who knows. And I think, I'm not sure how I want to do this. I think I'll do multiplayer before I do towers, because I think towers will be hairy. But the cool thing is I could create components and systems to control towers or anything really. They don't have to be enemies. As you could see, I had some references to something called enemy component. I could change that to be a more generic component, not particularly specified for enemies. So I could have certain behaviors be shared between enemies, towers, friendlies, whatever, easily. So now I think I should get going with the controller support. There were some issues, you can see. I don't have the sensor thing for the enemies. I'm gonna add as a backlog thing here. Fix enemy sensors noticing. But those are like nice to have stuff. And there was also the fix enemy direction system. So that's all I got for today. This video is way too long for you to be able to extract any information from it. Maybe I'll be able to edit down a special version of it all, where I just show you the system, and you could also always have a look at the code. Cheers.